reaction, addition reaction of alkynes. So second one, addition, addition of alkynes. As we have seen in the case of the alkenes, here also alkynes are unsaturated compounds. And so they undergo the addition reactions because addition reactions are characteristic reactions of unsaturated compounds. As you know, when an alkyne is made to react with a bromine water will be decolorized like alkenes. Bromine water, red bromine water will be decolorized. Similarly, alkaline potassium permanganate solution that is pink in color or violet in color, that is known as by S reagent. That is decolorized by alkynes also. Now let us see the addition of water. What are the products obtained? So addition of alkynes, say addition with water. Say alkynes can react with the water in presence of a catalyst. The catalyst is mercuric sulfate in presence of dilute sulfuric acid. Mercuric sulfate, Hg, mercury. Mercuric sulfate, HgSO4 in presence of dilute sulfuric acid. Then water molecule is added forming aldehyde or ketone. There will be the formation of aldehyde or ketone is formed. Addition of water gives aldehyde or ketone depending on the nature of the alkyne used. As we know, the aldehydes and ketones are collectively known as carbonyl compounds. Carbonyl, they are collectively known as carbonyl compounds because in aldehydes and ketones, there will be a carbonyl group, that is a C double bond O group. That group is called carbonyl group. It is there in aldehydes and ketones. For example, you take say aldehyde. In aldehyde, here there is a C double bond O H. C double bond O H. CHO group, aldehyde. And in ketone, there is a CO group directly. There is CO group. So both the aldehydes and ketones contain CO group. CO group is the same as the carbonyl group. So both these compounds contain CO group, carbonyl group. And so aldehydes and ketones are generally known as carbonyl compounds. So when alkynes, when react with the water in presence of mercuric sulfate in dilute sulfuric acid medium, there is addition of water forming aldehyde or ketone will be formed. Let us see the reaction. An example, you take CH triple bond to CH. Triple bond to CH, that's our ethine or acetylene. Ethine or acetylene. It reacts with water in presence of a mercuric sulfate, HgSO4, and the dilute sulfuric acid. There is an addition of water. Two hydrogen atoms are added to one carbon, and oxygen is added to another carbon. Two hydrogens are added to one carbon, and oxygen is added to the other carbon. The triple bond is broken. Only a single bond is remaining there. The two pi bonds are broken. And you get a compound, CH3, CH3, CHO, like this. Same as CH3, CH double bond O. Or CH3, C double bond OH. That is aldehyde. CH3, CHO. CH3, CHO is ethanol. The name of the compound, ethanol. This is a ethan all for aldehyde. Ethanol. In the common system, the compound is known as acetaldehyde. Ethanol or acetaldehyde, CH3CHO. An aldehyde is formed. Similarly, we take propane. Propane CH3, CH3, C triple bond, CH. That's our propane. Propane. Now, propane reacts with water. In, in presence of water, combines with water in presence of mercuric sulfate, Ng plus 2, and dilute sulfuric acid, H2SO4. Mercury sulfate, mercuric ions. As before, there is addition of two hydrogens to one carbon and oxygen to the other carbon. So, when hydrogen is added, hydrogen goes to the carbon bearing more number of hydrogen atoms, and oxygen goes to the carbon bearing less number of carbon atoms. So that the product is CH3, C double bond O, CH3, and this is the product obtained. Two hydrogens are added to the carbon bearing more number of hydrogen, that is CH. Two hydrogens are added to CH. So that CH becomes a CH3. And oxygen goes to the middle carbon and it forms a CO group. And this compound, that is our propan, this compound is a propanone. That is a propanone. The common system, the compound is called acetone. More details we can study next year. Propanone or acetone. Say acetone is a ketone, CO, ketone. See in the first compound, there is formation of the aldehyde group. And in the second compound, there is formation of the CO group, ketone. So aldehyde or ketone is formed when water is added to an alkyne in presence of a mercuric sulfate, HgSO4. Now, let us stop the reactions of the alkynes. Let us go to the last portion of organic chemistry, and it is our aromatic hydrocarbons. They are aromatic aromatic hydrocarbons. Aromatic hydrocarbons. You know, aromatic hydrocarbons are also known as arenes. Arenes. So arenes are aromatic hydrocarbons. And what are aromatic hydrocarbons or arenes? They are hydrocarbons, very clear. And these are the compounds, the hydrocarbon compounds, benzene and the related compounds. These are benzene and the related compounds, benzene-like compounds or the related compounds. The related compounds, benzene-like compounds or related compounds. These are known as arenes or aromatic hydrocarbons. See, aromatic hydrocarbons or arenes are benzene and benzene-like compounds. They need not be just like benzene. They have a property known as aromaticity. Aromaticity. The hydrocarbons which show the property known as aromaticity. The hydrocarbons which show the property aromaticity. Aromaticity. And what is aromaticity? Aromaticity. Aromaticity, the term aromatic is first originating from aroma. The term aromatic is first originating from the word aroma. Aroma means pleasant smell, sweet smell. Because the compound studied under this heading originally, they had a sweet smell, agreeable smell. And so they were known as aromatic compounds. That means the compounds which have aroma, that is sweet smell, pleasant smell. So, for example, benzene has a sweet smell.
Excuse me, sir.
Oh,
Sir, your video is off.
video പോയിന്ന്. Now, all right.
Yes, sir.
So, the word aroma, aromaticity or aromatic, it is coming from aroma. Aroma means pleasant smell, sweet smell. So, the sweet smelling compounds, in that sense, these compounds were originally known as aromatic compounds. But so that in the development of aromatic chemistry, we have a large number of compounds. Say they are not having smell. We have a large number of compounds which have foul smell also. So the original significance, that means the compounds with aroma or a sweet smell, that is lost. There are compounds which are not having smell at all. They are non-volatile. There are compounds with the there are compounds with a foul smell also, disagreeable smell also. So the original significance is lost. Now, the term aromatic is coming from aromaticity, a special property known as aromaticity. If we consider the formula of a molecular formula of a benzene, the molecular formula of benzene is C6H6. C6H6. Compared to the number of the carbon atoms, number of the hydrogen atoms, carbon atoms, the number of hydrogen atoms is very, very low. It is very, very low compared to the alkanes. Alkanes are CnH2n plus 2. The number of hydrogen atoms will be higher than that of the number of the carbon atoms. Then alkenes, CnH2n, the number of hydrogen atoms will be double the number of the carbon atoms. Alkynes, CnH2n minus 2, still the number of the carbon atoms is very high. But you come to benzene, C6H6, the number of hydrogen atoms is very low, and it shows that it is highly unsaturated compound. It shows the molecular formula shows that it is a unsaturated compound. But it shows the properties of a saturated compounds also. Definitely, benzene gives the reactions of unsaturated compounds, no doubt. Benzene shows the chemical properties of the unsaturated compounds. That is given by benzene. At the same time, benzene is not that much reactive as our alkenes and alkynes. It is very stable. It has extra stability, although there is a high degree of unsaturation. And it behaves as a saturated compound. The main reactions of benzene are related to the reactions of saturated compounds. That means benzene shows the properties of unsaturated compounds, at the same time the properties of saturated compounds also. Secondly, benzene has a high degree of say stability. It is highly stable. It is it is not that much reactive. For example, if say chlorine water is added, that is not decolorized. It's not decolorized by benzene. If a small amount of potassium permanganate solution is added, that is not suddenly decolorized by benzene, although there is a high degree of unsaturation. So the unsaturation in benzene is something different from the normal unsaturated molecules. It becomes a benzene becomes more stable, and the so-called aromatic compounds have extra stability. And that extra stability attains, that is called aromaticity. And what are aromatic compounds? Now, we can define aromatic compounds like this. That is based on Huckel's rule of aromaticity. Huckel's rule, Huckel's rule, Huckel's rule. And what is Huckel's rule regarding aromaticity? The rule is very simple. Say, according to Huckel, the scientist Huckel, planar conjugated polyenes. Say, planar. The system should be planar. It should be planar. The molecule, or maybe an ion also. An ion also. The species should be planar. So planar conjugated, conjugated, conjugated polyenes, poly, polyenes. Shall I explain what it is? Conjugated polyenes with 4n plus 2 pi electrons. 4n plus 2, 4n plus 2 pi electrons. 4n plus 2 pi electrons. And complete delocalization of the pi electrons. And complete delocalization, complete delocalization, complete delocalization are aromatic. Such compounds are aromatic. Let me explain each term. So what are aromatic compounds? Or which compounds can show aromaticity or aromatic character? Or whichever compounds are to be named as aromatic compounds? The rule is this. Huckel rule is this. Planar conjugated polyenes. The molecule or the ion, it should be a planar one. Planar conjugated polyene. You know polyene. What is the meaning of polyene? Poly means more than one poly. Ene. What is ene? Ene, double bond. Carbon-carbon double bond. So polyenes, that means more than one double bond. More Carbon-carbon double bonds, polyenes, more than one double bond. Conjugated. What is the conjugation? That means alternate. Alternate. Single bond, a double bond, single bond, a double bond. It's conjugation. Conjugated polyenes with a 4n plus 2 pi electrons. N is an integer 1, 2, 3, 4, etc. Any integer 1, 2, 3, 4, etc. So planar conjugated means alternate. Alternate polyenes. Alternate double bond. Single bond, a double bond, single bond, a double bond, single bond, double bond. That is a polyene. Conjugated polyene. Planar conjugated polyenes with 4n plus 2 pi electrons. With a 4n plus 2, 4n plus 2 pi electrons. If pi bond is there, pi bond is there, the electrons present in the pi bond are called pi electrons. Carbon-carbon double bond, one is sigma bond, other is a pi bond. One is sigma bond, the other is pi bond. Sigma bond, biaxial overlap. A pair of electrons is shared. Pi bond, that is lateral overlap, sideways overlap of the orbitals, p orbitals, parallel p orbitals. They are also a pair of electrons is shared. But the overlapping between the orbitals different. The sigma bond, there is coaxial overlap. But in the pi bond, there is sideways overlap, lateral overlap. That's the difference. So in the pi bond also, there will be a pair of electrons. A pair of electrons is shared. And the electron pair present in the pi bond is called a pi electron pair. Pi electron pair. So 4n plus 2 pi electrons. And these electrons are completely delocalized. Delocalized means the pi electrons are not localized between any two carbon atoms, common to all the carbon atoms. The pi electrons are common to all the carbon atoms. And such a system may be a neutral molecule or it may be an ion also. That is known as aromatic compounds. That property is called aromaticity. They are called aromatic compounds. That is the modern definition given. So according to Huckel's rule of aromaticity, aromatic character, planar conjugated polyenes with the 4n plus 2 pi electrons and a complete delocalization of the pi electrons are aromatic. Systems are aromatic. Let us take the case of benzene. You know, benzene, molecular formula C6H6, that is known to us. Do you remember the structure of benzene? You have studied this in the beginning and you have studied this in the 10th standard also, carbon compounds. So in benzene, there is a ring of six carbon atoms. A ring of six carbon atoms. Hexagonal ring. Hexagonal ring. A ring of six carbon atoms. Say like this. Then C6. Hydrogen atoms, say one electron each on the carbon atom. So C6H6. This is planar. And what about the hybridization? In benzene, in benzene, the hydrogen atoms, they have sp2 hybridization. Sp2 hybridization. So here there is single bond, say double bond, single bond, Kekulé structure. That's our Kekulé structure. And this is a conjugated system. Say single bond, double bond, single bond, double bond, single bond, double bond, like that. Conjugated system. Say polyene, polyene. There are three double bonds here. So it is a polyene. Not only that, this molecule is a planar molecule. It is planar because all the carbon atoms have sp2 hybridization. All the carbon atoms have sp2 hybridization. So the angle will be 120 degrees, triangular, 120, triangular planar, triangle sp2, sp2, trigonal planar, triangular planar, 120 degrees. All are having the trigonal planar structure. So that this molecule is planar. So benzene is a planar molecule. It is a conjugated system, alternate single bond and double bond. And polyene, there are three double bonds, 4n plus 2 pi electrons. Let us check that. 4n, 4n plus 2 pi electrons, where n is equal to 1, 2, 3, 4, etc. If it is equal to 1, 4 into 1 plus 2 is equal to 4 plus 2 is equal to 6. Now you count the number of pi electrons present in benzene. See, in benzene, there are three pi bonds. See here, 1, 2, and 3 pi bonds, double bonds. In the double bond, only one is sigma bond, other is pi bond. The two bonds are not identical, that we know. So there are three pi bonds. In three pi bonds, there will be 3 into 2, 6 electrons. See, the number of the electrons, 6, pi electrons, 6. That is in agreement with the 4n plus 2 rule. 4n plus 2 pi electrons. And so it is a, benzene is an aromatic compound. That is an aromatic compound. Okay. So any system of this type, any system of this type can be an aromatic system. It need not be a molecule, a neutral molecule like benzene. It can be an ion also. Okay. And completely delocalized. We have seen the phenomenon of a resonance. Phenomenon of resonance. Due to resonance, the electrons are, the positions of the pi electrons will be changing. And it gives another Kekulé structure. It gives another Kekulé structure. Do you remember that? In resonance, we have studied that. There is another Kekulé structure. That means the position of the double bond is changed. The position by electrons are changed. So delocalization, say like this. Another structure. Kekulé 1, Kekulé 2, two different structures are given. In the next instant, what happens? The pi electron pairs are again shifted, and that gives you the the first structure. So it goes on. That means the electrons are not, pi electrons are not localized between any two carbon atoms. It is a delocalized, like the pi electrons are delocalized electrons. So instead of giving alternate single bond and a double bond, we can show the pi electrons by making or marking a circle, daughter circle or a solid circle. And why does it happen? Say there is pi bond, we know, and the pi bond is formed by the, the sideways overlap. Let us think of the sideways overlap of the p orbital. See here, a ring of 6 carbon atoms, and there will be parallel p orbital. See like this, perpendicular to the plane. Perpendicular to the plane, there will be parallel p orbitals. When A pi bond is formed between these two. These two. There is a sideways overlap of the two p orbitals shown like this. So the pi bond is between these two carbon atoms. At the same time, here there will be the sideways overlap like this. Okay. And here also there will be the sideways overlap. These are the three pi bonds. But remember that the distance between the carbon atoms, the distance between the carbon atoms, that is the same. In benzene, the distance between the two carbon atoms is the same. So the possibility for the sideways overlap is not localized. All the p orbitals, they are parallel. All the parallel p orbitals are equidistant. So what happens? All the p orbitals will be touching each other. Have you seen before you begin, say, cricket? This is the time of cricket. Cricket. What the cricketers do? All of them will be forming a circle. No, eh? I don't. We don't know what is going on there. Okay, whatever it is, eh? They are forming a circle and they are joined together. Similar thing happens here also. So the formation of the pi bond. That is equal. There is equal possibility. There is a equal possibility for the sideways merging of the p orbitals, and that is called a delocalization. See here, here, then see all the p orbitals are parallel to each other. All are parallel to each other, and the merging will be, see, the upper side. See, the upper side are merging, forming the pi bond. Upper side of the p orbitals are merging like this. Similarly, here also the upper side of the ring are merging together. See, that is equidistance. Similarly, you think of the bottom side. See, the bottom side, these are merging together. Bottom side. So the pi electrons are not localized. The pi electrons are completely delocalized electrons. Localized means they are trapped at a locality. They are confined at a locality that is localized. They are confined between two carbon atoms, any of the two carbon atoms. It is not like that. All the parallel p orbitals, they are equidistant, and the sideways overlapping will be equal. The possibility for sideways overlapping will be equal. And therefore, all the pi electrons, all the pi electrons they will be, say, forming an electron cloud, say, upper side. Upper side, there is an electron cloud. And at the bottom side also, there is a electron cloud. That is electron cloud. That means all these pi electrons are delocalized, complete delocalization are delocalized electrons. So a ring of cis carbon atoms, and on the ring there will be 6 dumbbells perpendicular to the plane, and they will be merging up and down with equal possibility, and all the 6 electrons are completely delocalized. And due to this delocalization, an extra amount of energy is given out. That is called a delocalization energy. And the resonance people call it as resonance energy. Delocalization energy, that is according to molecular orbital theory. And according to resonance, it is called the resonance energy. So an extra amount of energy is given out from the system, and it will be more stable. So the system becomes more stable. due to the release of a resonance energy or a delocalization energy. More the energy lost, more stable the molecule or the system is. So such a system can be an aromatic system now. It need not be the aromatic ones. That means the ones with the agreeable smell. Okay, let me take some examples for this. Among the aromatic hydrocarbons, the first one, as you know, C6H6, and it is our benzene aromatic hydrocarbon. The simplest one is benzene. You take another one in which one of the hydrogen atoms is replaced by a methyl group from C6H6. One hydrogen is replaced. For example, from the top carbon, one hydrogen is replaced by CH3 group, and it is a C6H5, C6H5, CH3. The compound is methyl benzene. That's our methyl benzene. Methyl CH3 group is the methyl group. Methyl group. So compound is methyl benzene. And the very common name is toluene. It is commonly known as toluene. C6H5CH3, methyl benzene or toluene. Methyl benzene is the strict IUPAC name, but toluene is also accepted by IUPAC. IUPAC. So all these compounds, these two compounds contain only one ring. There is only one aromatic ring. The ring is aromatic. The benzene ring, that is aromatic. CH3 is not aromatic. The benzene ring is aromatic. There is only one benzene ring in this. If there is only one ring like this, then it is called, say, a mononuclear compound. Mononuclear or uninuclear compound. There is only one nucleus. Nucleus means the ring. The ring is known as, in the aromatic system, the ring is known as the nucleus. Nucleus of the compound. There is only one ring, aromatic ring, or a one aromatic nucleus. Then it is called a mononuclear or a uninuclear. Mononuclear. Mononuclear aromatic compound. Aromatic compound, mononuclear. There is only one aromatic nucleus. Let us take some more examples for polynuclear systems. Polynuclear. In the polynuclear aromatic compounds, we have seen that already. There will be two or more rings fused together. They are called the polynuclear aromatic compounds. Polynuclear aromatic compounds. Polynuclear aromatics. For example, polynuclear aromatics. For example, say two benzene rings are fused together like this. C6H5, C6H5. That is delocalized electrons. Instead of the alternate single bond and a double bond, you can draw a circle. That is to show the pi electrons. Because some of the electrons are delocalized electrons. There are three pairs, 6 electrons are there. 6 electrons are there. There is no doubt. And C6H5. And the other group is also C6H5. C6H5 group is called a phenyl group. Phenyl. Phenyl. Here there are two phenyl groups joined together by means of a covalent bond. And this is called a diphenyl. Diphenyl or biphenyl. Biphenyl. Diphenyl or a biphenyl. There are two aromatic nuclei. Two benzene rings are there. So it is a dinuclear or a binuclear compound, polynuclear in general. So the compound is a diphenyl C6H5. That group is called the phenyl group. So it is coming from phene. Phene. Benzene has a very old name, phene, Phene, phene. From that we have the group phenyl group. Phenyl group. Okay. So diphenyl, there are two phenyl groups. Diphenyl. Instead of this, if two benzene rings are fused, say like this, side by side, there is a common side. Two benzene rings are fused together. That is also bimolecular, nuclear or dinuclear, polynuclear. And this is called naphthalene. It is a naphthalene. 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 Two benzene rings are fused together. That is naphthalene. It's a polynuclear aromatic hydrocarbon. Suppose three benzene rings are fused together. We are taking some examples. Say benzene ring 1, benzene ring 2, then benzene ring 3. Three benzene rings are fused together. Then it is called anthracene. 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 Three nuclei are there. Anthracene. Anthracene. That is also a polynuclear compound. Okay. Now let us take some examples to show isomerism in aromatic compounds. For that, we may take silenes as an example. Silene. So what are silenes? Silenes. Silenes are dimethyl benzenes. Dimethyl, dimethyl, dimethyl benzenes are xylenes. Silenes are dimethyl benzenes. They are silenes. See, have the benzene ring, then there is a methyl group, then it is called toluene or methyl benzene or toluene. Methyl benzene or toluene. Now, the second methyl group that may be here, CH3, or second methyl group. It changes its position. It changes its position. It changes its position. Okay. Changes its position. I repeat this. Changes its position. See, we get another isomer. All these are isomers. And if you change this to this carbon, there is no change because it is a repetition of the second one. So one, two, and three isomers are possible. Three isomers are possible for xylene. Xylene is dimethylbenzene, dimethylbenzene. And the three isomers, there are three isomers. In the first isomer, the methyl groups are adjacent to each other. But in the second, the methyl groups are, say, alternate. Positions will be alternate. And in the third one, say here, third, sorry. In the third one, the methyl groups are at the opposite positions. Opposite position. And how to name this? All these are dimethyl benzenes, no doubt. IUPAC system. And we can number these carbon atoms. Say 1, 2, 3, 4, 5, and 6. 4 and 5 and 6. The carbon atoms are numbered like this. If it is so, the first compound is dimethylbenzene, but the methyl groups are on the first and the second carbon atom of benzene ring. And so it is named as 1,2, 1,2 dimethyl 1,2-dimethyl benzene. 1,2-dimethyl benzene. If it is so, what about the second compound? Second compound. Second compound is, you can write the name now easily. It is a 1,3-dimethyl, 1,3-dimethyl benzene. The 1,3-dimethyl benzene. Come to the third one. 1, 2, 3, and 4. So the compound is 1,4 dimethyl, 1,4 dimethyl benzene, 1,4 dimethyl benzene. Suppose the methyl group is on the fifth carbon, the fifth carbon. It is similar to the second structure. Suppose the CH3 group is on the sixth carbon. That is the repetition of the first one. First one. So there are only three isomers like this. And this is the IUPAC name of the various isomers of silanes. 1,2-dimethyl benzene, 1,3-dimethyl benzene, 1,4-dimethyl benzene. In the common system, these compounds are named as, say the first one is called ortho, ortho, orthoxylene, ortho, orthoxylene. We can write it as small o hyphen xylene, orthoxylene. The position, 1,2 position. Similarly, 1,6 position. This ortho position. Orthoxylene. The other one is called metaxylene. That is the common name. Small m for metaxylene. Metaxylene. And the third one, that's called paraxylene. Paraxylene or small p, xylene, paraxylene, orthoxylene, metaxylene, paraxylene. We must study the positions ortho, meta, para. Ortho, meta, para positions. Say 1,2 position or 1,6 position, ortho. 1,3 position or 1,5 position, meta. 1,4 position, it is para. Para. So ortho, small o. Meta, small m. Para, small p. Orthoxylene, metaxylene, and paraxylene. The three isomers of a xylene. Is it clear now? Now I am going to ask you a question. Lydia. Lydia, say what type of isomerism is shown by these three isomers? Come on. Yes, come on. You say something. You said?
No,
No. You think of the various possibilities, isomerisms you have studied. Huh? Huh? You can't. Achyut, what is your opinion? What is the type of isomerism? I heard repeated the word a number of times. You cannot. You just think of the various types of isomer
Structural, sir.
studied. Come on.
Structural.
Structures are different. That is a common term. Structures are different. But in structural isomerism, we had seen subdivisions. One is a carbon skeleton. that is a nuclear isomerism or chain isomerism. Then functional group isomerism, different functional groups. Position isomerism, different positions, different positions. Now you come to the conclusion. You say, what is the type of isomerism? We cannot see. You look at,
Position.
come on.
Position isomerism, sir.
Yes. Why doubt? Lydia, it is a position isomerism. That is why you repeated the term, the positions of, the positions of, the positions of. Methyl groups are different. Positions of methyl groups are different. That is to screw the idea into you. See? So these are position isomers. These are the position isomers. Here we have no functional groups, but here we have the side chains. Side chain. See, the methyl group is called a side chain. This is side chain. The benzene ring is the nucleus. Benzene ring is the nucleus of the compound. Nucleus. And the other carbon groups, they are called side chains. Side chains. Side chains. So the positions of the side chains are different. Okay. The positions of the side chains are different. Not the positions of the functional groups. Instead of the functional groups, the we have only the side chains. So the positions of the side chains are different. So these are called the position isomers. CH3 group is called the side chain. There are two side chains in this molecule. Benzene is the nucleus and CH3 group, that is side chain. Okay, in this context, let me take another example. Say, you have seen this compound already. That's our toluene. And we have seen another compound just now, CH3, CH3, that is xylene, orthoxylene, orthoxylene. We can take another compound that is ethyl benzene, CH2, CH3, ethyl benzene. Here, in all these cases, the CH3 group is a side chain and the rest is the nucleus, aromatic nucleus. Here there are two side chains and the CH3, CH2, ethyl group, that is also side chain. All these are side chains, side chain, say side chain, side chain, and this is a side chain. The carbon atom is directly linked to the nucleus, benzene nucleus, and they are the side chains. Okay. Now, let us take another example, say a compound like this. There is benzene ring, and here there is a OCH3 group, OCH3 group. Okay, let me say that this molecule, this molecule does not have a side chain. This molecule, we have to study this second year. This is a anisole, an ether. So this molecule has no side chain. This has no side chain. There is CH3 group. There is CH3 group, but that is not regarded as this CH3 group. That is not regarded as a side chain. Now, can you say if a carbon group is named as a side chain, what is the peculiarity of the bonding? I say the first three compounds, there are side chains. But in the fourth compound, the CH3 group is not a side chain. What the difference you can see here, Nandana? What the difference you can see in these structures? The first compound, CH3 group is a side chain, I told. Second compound, CH3 groups are side chains. Third compound, CH2CH3, that's also a side chain. But in the fourth compound, OCH3, there is CH3, but that CH3 is not a side chain. Why? So the first three are called side chains, and the fourth one, that is not regarded as a side chain. So if a carbon group is to be treated as a side chain, there should be a peculiar type of bonding. There should be special bonding. What is it? What is the difference you can see here? What out of the CS3 group in the last compound? CS3 group. And in the other compounds, CS3 group, the bonding with the nucleus, benzene nucleus, what the difference you can feel? Diya, what do you say?
There is O group.
O group is there. Okay, just wait there. See in the first compound, CS3, second compound, CS3, third compound, CS3, and fourth compound also there is CS3. But then, try to explain. You try. Let it be wrong or right. It doesn't matter. Try. What is special with this? Oxygen is
Before CH3 group, it is connected to O group.
CS3 group is attached to O group. And what about the linkage between the benzene nucleus and the CS3? The bonding of the CS3 group with the benzene ring is directly linked. The
It
CS
is not directly linked.
not directly linked. The last compound, the CS3 group is not directly linked. So a carbon group is known as a side chain if the carbon group is directly linked to the nucleus. Maybe CH3, maybe CHO, whatever it is, it should be directly linked to the nucleus. Say, you take a compound like this, say C6H5, then C double bond O H. It's an aldehyde. 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 The aldehyde group is also a side chain. It's a side chain. Because the carbon atom of the CHO group is directly linked to the benzene nucleus, aromatic nucleus. Here, the carbon atom of the so-called carbon group of the CS3 group, that's not directly linked to the benzene nucleus. So, if carbon is directly linked to the not only benzene nucleus, any aromatic nucleus, any aromatic. So, for example, naphthalene. Naphthalene, we take naphthalene, say CH3. Here also, naphthalene, CH3 group is directly linked. Okay, whatever it is, that is methyl naphthalene. The methyl group is directly linked to the aromatic nucleus. So, the owner for side chain is lying in the bonding between the side chain carbon and the nucleus. The carbon is directly linked to the nucleus, aromatic nucleus. Maybe benzene, naphthalene, anthracene, whatever aromatic nucleus it is, the carbon atom is to be directly linked, then only it is treated as a side chain. Clear? You say yes or no, all of you.
Yes, sir. Yes,
Sir,
sir.
Important because next year there will be a number of side chain reactions. Side chain oxidation reactions will be coming there. Number of reactions. In that case, the definition of side chain should be there in your mind. I'm not giving you any notes on this. You just uh, you just mark it in your mind itself, in brain itself, your memory. You keep it there. For side chain, the carbon atom should be directly linked to the nucleus. Then only it is a side chain. Okay. So there is a difference between the side chain. Now, we have seen aromatic compounds, aromatic hydrocarbons, arenes, Huckel's rule, etc. Now, let us take one compound from the aromatic series, that is benzene. Let us go to benzene, C6, H6, benzene, C6, H6, benzene. We know the structure of benzene. A number of times you have drawn the structure, two Kekulé structures. The two Kekulé structures are this. There will be alternate single bond and a double bond. And it is resonating to the other structure, the other structure. The pi electrons will be delocalized. I'll get a structure 2. It's just a Kekulé 1, Kekulé 2. And it is going on like this. So ultimately, what will be the actual structure? It is a hybrid of all this. And the pi electrons are delocalized electrons. So instead of drawing alternate single bond and a double bond, we can draw this structure, the resonance structure. Instead of that, you can draw a solid circle also. See, to show the structure of benzene. Remember that it is a chain of 6 carbon atoms. A chain of 6 carbon atoms. What we have drawn is the bond line structure. Say bond line structure. See, it is like this, the actual structure. The complete structure is this. And we have drawn only the bond line structure. There will be 6 carbon atoms at the corners of the hexagon. At the corners of the hexagon, there will be 6 carbon atoms. And on each carbon atom, there will be 1 hydrogen atom. The pi electrons are completely delocalized pi electrons. So instead of drawing the conjugated double bonds, alternate single bond and a double bond, conjugation. Instead of that, you can draw a circle showing the 3 pi electron pairs, 6 electrons are say shown delocalized completely. So can draw the structure like this also for benzene. That is the easiest structure. Okay. Now let us think of the preparation of benzene. Now benzene can be isolated from coal tar. It can be isolated from coal tar. Coal tar. The distillation of coal tar. What is coal tar? Coal tar is a fraction obtained by the distillation of coal. Coal is heated in absence of air. Coal is heated in absence of air. Coal is the natural form of carbon that is mined out, Kalkari. Kalkari, coal mines, so that is mined out. Then it is heated. Then coal is not directly used as the fuel because it contains a large number of other compounds. Usually coke is used as the fuel. Coal also can be used. Coal also, low grade coal also can be directly used the fuel, no doubt. But usually we separate the other carbon compounds from coal and we get the carbon residue that is called coke, and that is used as the fuel. Okay. So when coal is heated in absence of air. Coal is decomposed into different fractions. Coal gas, coal gas, the gaseous products, coal gas. Then coal tar, another fraction obtained from coal, coal tar, ammoniacal liquor, ammoniacal, ammoniacal liquor, ammoniacal liquor, and finally coke. That is the carbon residue used. So we get four different fractions. And this is called the destructive distillation of coal. Destructive distillation of coal. So from coal, the freshly mined out coal is heated in absence of air. That we get different fractions like coal gas, that is the gaseous products. Coal gas is the gaseous products. That is mainly used as fuel. Mainly used as fuel. Okay, coal gas, coal tar. Coal tar is the reservoir of a number of aromatic compounds. A number of aromatic compounds, coal tar. Ammoniac liquor. It is ammonia and ammonium salts. Ammonia and ammonium salts. You know the uses of ammonia and ammonium salts. They are used especially in the fertilizer industry. Nitrogen fertilizers, ammonium sulfate, factum phosphate, etc.
Sir,
Ammoniac liquor.
sir, I have a doubt.
uh,
Sir, in thermal power plants, actually, what do they use? Is it
Usually,
coke?
you can use the low grade coal itself, or they can use coke. Coke. If it is a low grade coal, coal, it is directly used because there is no meaning. It is not economical when we do the destructive distillation. Okay. So they use either low grade coal directly or they can use coke. Coke is used usually. Coke. So coke is burnt, then steam is produced, then steam is used to rotate the turbines instead of water. You know, the hydroelectric project, we make use of the energy of water. So instead of water, he make use of steam. Steam is produced. And for the production of steam, we'll burn coke usually. Or you can use coal itself directly can be used, usually coke. So from coal tar, I told you it's a reservoir of a large number of aromatic compounds. You need not go deep into that. Say coal tar from coal tar, benzene can be separated. Okay. Let us think of the laboratory method of preparation of benzene. Let us see three methods. Preparation of benzene. Aromatic lab method. One is from acetylene, the polymerization of acetylene or ethylene or acetylene, polymerization of ethylene. You know what is polymerization? It's a combination of simple molecule, a large number of simple units forming a large molecule, a macromolecule. That's called the polymerization. The simple units or units are called monomers, and the macromolecule, the large molecule, that's called the polymer that we have seen. Yesterday we had seen that. Okay. Here, let us think of the polymerization of ethylene or acetylene. When acetylene is passed through, ethylene is passed through red hot iron tube, C2H2, that is passed through red hot, red hot iron tube, iron tube. There is polymerization. Cyclic polymerization. Cyclic. This is a cyclic polymerization. No, in polythene. Do you remember? CH2, CH2, one ethene molecule. CH2, CH2, second ethene molecule. CH2, CH2, third ethene molecule. One after the other, just like our goods train, the compartments, the bogies of a train. Not only goods, we are also goods. So the train compartments, one behind the other, it is linear. Linear. We'll study more about this next year. Linear. One after the other. It is linear. Now, the polymerization can take place with a cyclization. ring closure. Ring will be formed. This is not a cyclic compound. This is an open chain compound. Open chain structure. It's linear. And there can be the ring structure, that is C6, H6. The cyclic polymerization. Three molecules are combined together forming benzene C6H6. So cyclic polymerization. Cyclic polymerization, because a ring is formed. A ring is formed, and so it is cyclic polymerization. Okay, cyclic polymerization. How many molecules are used here for the polymerization? Three molecules. The monomer is C2H2 ethine, or acetylene is the monomer. Say monomer, this one. This compound is this is the monomer. Monomer. While this is the polymer. It's a cyclic polymer. Same polymer. In the polymer, it's benzene. In the polymer, how many monomer units are combined? How many monomer units are combined? Very clear. Three monomer units are combined. And so it is called trimerization. 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 Three molecules of the monomer are combined. And so it is a trimerization. Three mer parts. Three parts are combined. Trimerization. Cyclic trimerization. Cyclic polymerization. That gives us a, say, benzene. This reaction we had to study under the heading ethine. But very purposefully, I left it there because we have to take it here again. That is the specialty of organic chemistry. We need not repeat this. The reactions will be repeated, but you study it only once, and that can be used, say, a number of times at a different contexts. Okay, that is one method. Second one is the decarboxylation reaction. Decarboxylation. Decarboxylation. For decarboxylation, what we have to do? You take the sodium salt of a carboxylic acid. And which is the carboxylic acid to be taken here? The carboxylic acid is C6H5 COOH. C6H5 COOH. That is the carboxylic acid used. And this carboxylic acid, that is called benzoic acid. Benzoic acid. Benzoic acid. C6H5COH. The benzene ring, the one of the hydrogens is replaced by COOH group. C6H5COH. It's benzoic acid. Now, you take the sodium salt of benzoic acid. It is a C6H5 COONA. And this is a sodium benzoate. Sodium benzoate. Benzoate. Sodium benzoate. The sodium salt of benzoic acid is called a sodium benzoate. C6H5 COONA. Sodium benzoate. And this is heated with what? You don't remember? Soda lime. That is heated with the soda lime. What is soda lime? NaOH, soda, caustic soda, plus lime, CaO, quick lime. That is soda lime. Soda lime. Then what happens? The COOH group is removed. The COOH group is removed. And so it is called a decarboxylation. The carboxyl group is removed. It's called a decarboxylation. And you will get C6 H6. C6 H6 benzene is formed. C6 H6 by the destruction of the carboxyl group, by the removal of the carboxyl group. What will happen to the carboxyl group? COONA, that will be converted to Na2CO3. 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 You get a benzene C6H6 by the decarboxylation of the sodium salt of benzoic acid. Sodium salt of benzoic acid. Benzoic acid is C6H5COOH. Sodium salt is C6H5COON. And it is named as sodium benzoate. And it is heated with the soda lime. NaOH plus CO. Then the carboxyl group is removed. So it is called a decarboxylation. That is formation of the original hydrocarbon. The COH group is removed and it is reduced to the original hydrocarbon C6H6. So it is a decarboxylation of benzoic acid or sodium benzoate to form benzene. Okay, let us take one more reaction. And it is the third one is zinc dust distillation. Zinc dust distillation. Distillation of phenol. Zinc dust distillation of phenol. Phenol, that is a C6H5OH. 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 It is phenol. Phenol. C6H5OH. Phenol. Now, the name coming from phen plus ol. Do you remember? In the last class, I told you benzene has a very old name, phen, phen, plus ol for OH group. So phenol. Okay. You need not remember all these things. So phenol is heated with the zinc dust. Zinc is acting as a reducing agent. It is acting as a reductant. Oxygen is removed as ZnO, minus ZnO. Minus ZnO means that's a product. That's a product. And I am writing only the important product, C6H6. C6H6. Benzene is formed. And the reaction is called soda lime distillation of phenol. Soda lime distillation of phenol. The oxygen is removed. Oxygen is removed with the formation of a benzene. So these are the next year we have to study. You have to study. Okay, make a correction. You have to study phenol. Then this reaction will be coming there. Next year you have to study. Oh, again the term we you have to study benzoic acid. Benzoic acid. And also this reaction will be coming there. Okay. But all these reactions will be repeated there. So we need all these reactions in second year also. So these are some of the methods for the preparation of a benzene in the lab. Okay. Next, what happened to you, all of you? Eh? All of you are tired, gone to sleep. Oh, waking up. It is the time for lunch. Dinner is ready. Dinner is ready. Wake up, all of you, please. Malavika, Radhika, Emmanuel. All of you, please wake up. The lunch is ready. Move to the dining hall. Emmanuel is so tired. It is ready there. Yeah. Now, yes, pleasant. Yes, become pleasant. It is ready. Go and have it. And get ready for the next class. By next class, we have to finish our organic. There is one more class. No. By that, we can finish. We have to see only, say, 3, 4 reactions. Very important reactions. These are, yeah, all the time I'm repeating this. All these are needed for the second year, these reactions. So by that we can finish it. Emmanuel, Emmanuel, so hungry. What happened to Nia? Nia, she has already gone. Alvin, you are there or not? Michael, okay. We have 5 minutes more. 5 minutes more. Okay, you go and have your lunch and get ready for the next class. Let me stop now.